Welcome. Hopefully we can have a good and uninterrupted stream today. Just so you know, with the class that I literally just had, like the last hour from 10:30 to 11:30, I had to reset the router in my house no less than 4 times over the course of that hour. So it seems entirely probable that that's going to be the case today. If you guys wouldn't mind letting me know in this chat if that occurs. The thing is, like, in order to notice that the stream is down, I'd have to be either on this page or looking at OBS, which, you know, I don't have that constantly open. Whereas this is like a pop-up, so yeah. Yes, I did get a haircut. It's rather severe. This is my cove cut for this month. You know, you can see my lovely enormous forehead now. But I'm not self-conscious about my enormous forehead. Anyway, let's do some programming and stuff. Yeah? Cool. Oop. Thank you. Oh, incidentally, maybe I should lead with, just so you guys know, the deadline for assignment 4 was extended to tonight at midnight. So you have to make your submissions for assignment 4 by tonight at midnight, or your submission will not be accepted. So please get your assignments in on time. Don't miss the deadline. It won't be good if you do. So anyway, so we were talking about assembly programming. If I remember correctly, we were just about to get into this kind of stuff. So, just to recap where we were talking about, first of all, this assembly program, which, pardon me, computes the sum of all of the numbers between, from 10 down to 0. This is the assembly code. This is the looping section. And we were just going through and explaining what each of the operations does. So, just so you know, there are some, oh my goodness. You know what? At some point in these slides I should put in a table of common operators. I haven't quite gotten to that yet. But they're kind of what you would expect. You know, add, sub, div, mul for division and multiplication. So, anyway. So this is the visual environment. This is what it looks like when you execute code inside of the visual environment. Keep in mind that visual is an emulator. So because ARM is it's an instruction set mainly for phones and tablet devices. In order to run that on an x86 environment, which is, you know, Windows, Mac, and Linux, generally speaking, anything with like an Intel or an AMD processor, we have to emulate the code rather than being able to run it directly, which is fine. It sort of gives us a nice little sandbox to be able to play in. So, for assembly programs, the way that you break an assembly program down into its parts is by columns. Fundamentally, you should think of an assembly program as being like a table. So the first column of this table will be labels. We're going to get to the purpose of labels today. Instructions. Instructions are the actual CPU instructions themselves. And then operators, which are required by the instructions. Good? Cool. The move operation moves the contents of one register into another. So that's the other thing, is that we are fundamentally dealing with registers and literals at this point. We're going to get into memory a little later on, but registers are the CPU's internal memory. In ARM assembly, you get 16 of these bad boys, but you shouldn't use all of them because some of them are reserved for specific things. But yeah, so the first operator must be a register because you have to, like, you can't move data into a literal value. That doesn't make any sense. The second operator can be either a register or a literal value. The equivalent in C is op1 is equal to op2, so a regular assignment kind of operation. Although in C, this generally means that you're storing this guy in the memory location specified by this guy, which is not something that's true in assembly language unless you go to unless you do more work to make sure that that's the case. Otherwise, everything just stays inside the registers. We have add. So add computes the arithmetic addition of operand 2 and 3 and stores it in operand 1. The C equivalent is op1 is equal to op2 plus op3. And then we get subtract S. So the thing about ARM assembly is that you get what are considered compound operators, or compound instructions. So this is a regular subtraction instruction with S specified. S, when you put the S suffix on an instruction, what that means is that you're allowing that instruction to also set values in the status register. So it's like sub plus status. We're going to get into what the status register is and what its impacts are on program control. But it is basically all program control requires the status register in order to make determinations about the state of the program. So when you allow the subtraction operator to write to the status register, what you're essentially doing is you're allowing that operation to serve two purposes at once. One is the actual subtraction operation, and the second is some control flow jiggery-pokery. I got a question. Apologies if I have already mentioned this, but are we going to have an ARM or C++ assignment, or is that going to be an exam question? So I'm actually still working on I'm still working on assignment 5. Assignment 5 is going to be the last assignment. We're not going to be able to have time for another one. Yeah. On assignment 5, there are a few assembly questions. So yes, there are going to be assembly questions on assignment 5, and probably there's going to be an assembly question on the exam. So yeah, this is stuff that you actually have to learn how to do. Sorry. But don't worry, my expectations for what you can accomplish in assembly code are going to be reasonable. I'm not going to expect you to be able to do anything more complicated than some of the easier questions on assignment 1 in C. So, you know, like basic arithmetic stuff. Like, can you write a loop? Can you write a if statement? Maybe can you write a for loop with a loop with an if statement in it? You know, that kind of stuff. It's not going to be super complicated. But any word on midterm 2? What time is it? What day is it? Jesus Christ. I'm shaking my magic 8-ball and it's saying try again next semester for a midterm 2. Probably what will end up happening, I don't know. I need to get mark on autograding the midterm one. Probably what will end up happening is that the marks for the midterm will, the second midterm, which will not exist. I don't think we're going to have time for it. Those will be distributed across the exam and the assignments and possibly the other midterm. I might just, like, split it 3 ways, but it's terrible. Anyway. You know, I had originally intended for this class to have 10 assignments and 3 midterms. How hilarious is that, eh? Anyway. I'll take a look at some of these details, and I'll have an announcement up for you guys on Avenue by sometime tomorrow. Anyway, so, I'm gonna sneeze. Or I'm not. Anyway, so then we get this curious other instruction, B and E. And you'll notice that the operand for that is not, in fact, a register or a literal value, but a label. This is a branching instruction. It is actually another compound instruction, branch not equals. We're going to talk about branches quite a lot, but what a branch instruction does is it jumps to the specified label if the status, in this case, if the status register, well, if a particular bit in the status register is set to 0. We're going to take a look about this. It reads the status register and then decides whether or not to jump to a particular label in the code. If the sub s instruction causes an overflow, the s suffix will set the overflow flag in the status register. This branch statement only executes so long as the status register is set to 0. Overflow will cause the branch statement to stop jumping back to the label, terminating the loop. This whole section is on how to do that, so would it be possible, if there isn't going to be a midterm 2, to have an optional assignment to take up some of those marks that need to be redistributed? Optional assignment. What do you mean by an optional assignment? Like, I'll probably, like, it depends. I'm not sure if I'm going to be able to cover the C++ material on the exam. There's no technical requirement for it in the course accreditation document, so I'm not sure. I'm not sure that we're going to cover it. Maybe I need to just read that document more carefully. But I'll probably provide some exercises for C++, regardless as to whether they're marked or not. You know, it would be a reasonably simple matter for me to just pull some questions out of the textbook and throw them up into a Jupyter file. But, you know, those would definitely be, if people were counting on midterm 2 to boost their mark, yeah, I'll work something out. I'll work something out so that people aren't penalized too heavily. Like, when I'm setting up the... okay, maybe here's an idea. Sometimes I see it done in courses that there are like 2 different weighting schemes for assignment tests in the exam, and the student gets the maximum of the 2. Generally speaking, that's normally the way that works is one of the marking schemes has a greater weighting placed on the exam, like something like a 60 or even like a 60% on the exam or something, so that like if somebody just does a Hail Mary on the exam, then they manage to come away with a decent grade on the course, even if they flubbed the assignments or the tests and all that. I could see doing something like that, but I don't know. I'm also open to suggestions, as is evidenced by the fact that we're talking about this right now. I don't know. Something like that, maybe? I don't know. It's a weird semester. Yeah. Anyway. So, just a quick word on registers and literals. In ARM architecture, there are 13 general-purpose 64-bit registers that can be interacted with. So there are actually 16, but 3 of those you don't want to touch. You can reference these as operands by name: R0, R1, etc. If you take a look in visual, these are the guys: R0 through R13. I guess that technically is 14, isn't it? There are also a number of reserved registers, such as the status register mentioned above. In ARM assembly, literals are prepended with the octothorpe character, which is the pound sign or the hashtag character. They obviously can't be written to, but otherwise function as you would expect. Literals exist, fortunately enough. So, let's see what we have to say here. Just add the weight to the highest marked assignment. See, the thing about that, Anthony, is like, immediately in my head I'm going, okay, sure, but pretty much everybody got 100% on assignment 1, and assignment 1 was not necessarily a very good test of whether or not you understood anything at all from the course. So, there's a balancing act to be performed. Oh, okay. Man, why didn't you write that in Sarcastica? The universal font, unless you don't want it to be one. No, I don't think that scheme is one that could be made to work in practice, because assignment 1 pretty much everybody aced because it was super easy and didn't even really require very much C knowledge. So that would just be giving the marks out for free, effectively. You have to strike a balance between forgiving, a forgiving grade scheme, but actually requiring, like, you can't just give marks out for free. At least that's my policy. My policy is always, like, every mark that you get, like, every mark that appears in your final grade should be something that you've actually earned. Which is why I don't do, like, participation marks or marks for, like math journals. I find the idea of a math journal to be detestable. Anyway, so go with the control flow. What were things like in the old days? I hear you had to compile things for different processors. Yeah, to compile your code you had to mail it to IBM. It took 4 to 6 weeks. Before garbage collection, data would pile up in the computer until the computer got full and you had to throw it away. Early compilers could handle code fine, but comments had to be written in assembly. C could only be written on punch cards. You had to pick a compact font, or you could only fit a few characters per card. C++ was big because it supported floppy disks. It still just punched holes in them, but it was a start. None of this is true. This is all lies, but it's funny lies. So, let's reject society's labels. Do you remember go-to statements in C? In assembly, that's all you got. That's right, folks. In assembly programming, all you have available to you are go-to statements. There are no if statements, there are no while loops. Like in C, you can add labels to your code by simply typing the name of the label in the first column. Here you go. You can either include an instruction on the same line or not. The assembler doesn't care. So this is a valid instruction, and this is also a valid instruction. Leaving a space can improve readability. It has the tendency to divide your code up into blocks, which are a little bit easier to read. We can move execution to any label using the B or branch instruction. This is also known as an unconditional jump. In the previous example, we asked the subtraction operation to write to the status register if underflow occurs. We then use a conditional jump to continue executing a set of instructions until such underflow occurs. This creates a loop. Loops are not a first-class they're not a first-class entity inside of assembly. They are sort of a meta-phenomenon that exists only because of the setup of the goto statements or the branch instructions that you yourself have designed inside of assembly language. We can send information to the status register manually by using the CMP or comparison instruction. So, in the previous example, we used subtract S in order to do this. In this example, in the example that's coming up, we're going to use CMP comparison to compare the values of two registers. The 32-bit current program status register, also known as the status register, keeps track of various pieces of information related to the execution of the current program. Much of this takes the form of status bits or flags. I hate it when I do that. Here is the status register. Here, each one of these boxes is a bit, and the positions of these bits within the register is indicated by the numbers. So the 31st bit is N, and notice this is big endian. So here are the important ones. N is negative. It indicates if a value is negative. Z or 0 indicates that an appropriate instruction produces 0 as a result. C or carry indicates that an operation requires borrowing, as in subtraction. And V or overflow is set if the result goes beyond the range of numbers that can be represented in a signed 2's complement format. The rest of these guys are unimportant, at least in this class, but in case you're interested, I and F are hardware interrupts. T is thumb mode, which is a thing that exists in assembly mode. Thumb mode is like reduces the size of registers and everything so that you can run it using very few resources. And M4 through M0 are mode bits, mode of operation bits, which, again, don't really matter for our purposes. Honk. So, in ARM assembly, the B instruction has a number of suffixes, similarly to how you can add an S onto the end of the subtraction operation. You can add any of the following onto the end of the B instruction, and the following, it provides a range of different types of reading of the status flags that produce each of the comparator operators that we are used to using in C. So, if you want to test for equality, your suffix is EQ. All that does is check the Z flag to see if it's 1. I'm not going to do all of these. It's just for your interest's sake. You don't have to memorize these. All you have to be able to do is look up which operation you want to perform and use the correct suffix. That's what your take-home is. But you've got equality, inequality, signed greater than, signed less than, signed greater than equals, signed less than equals, negative, positive, always execute, never execute, signed overflow, no signed overflow, and then unsigned, greater than, less than, greater than equals, and less than equals. So notice, number one, signed comparisons are different. They are different instruction codes. So signed and unsigned have different instruction codes. This is interesting, and it's because, signed and unsigned values have different implementations in terms of, they have different interpretations inside of the CPU itself, so it makes sense that they have different instruction codes. In the same way, if you start working with floating point numbers, all of the floating point numbers have their own instruction codes for things like addition and subtraction and all the rest of it. So yeah, we're not really going to talk about floating point very much. We're going to stick to integers. But yeah, we can deduce from this that comparison R0, R1 sets status registers by subtracting R1 from R0. So it performs, so what it does is it subtracts R1 from R0, updates the status registers, updates the status flags in accordance with that operation, and if you get, overflow, then you can use the overflow condition, etc., etc. But it doesn't actually keep or store the results of that subtraction. The results of the subtraction itself are just kind of lost to the ether. All we're interested in here is setting the status register. Question. I think it would be really helpful for us to see you write a program in ARM and explain what you're using and why. I don't know if that's going to happen. So we're going to do that, I think, next. Yeah. Although if you want to see me construct it from scratch, that's also a thing. So, okay. All right. Let's see here. Let's see if I can do this from memory. So let's say that we had, let's say we wanted to write, I think I'm going to remember this from memory. We have the R2 register. Let's say we wanted to write 1 into that if the values in R1 and R0 are the same, and 2 into it if they're different. So let's first move into R0 some value 8, and let's move into R1 some other value 9. So they're going to be different to begin with. We would then compare R1 and R0. We can actually execute this and see what the value of the status register is at the end. So we can see Z, which is 0, which is these things are the same, that's currently set to 0. However, if we make these two the same and execute that up to that point, you can see that Z is set, and so is carry. So we can use that. Let's make two labels. Let's say true and false. So if this is the same, branch EQ, then we can go to true. If not equal, so branch not equal, we go to false. Then inside of here, we will move into R2 the value of 1, and here, that's not it. There we go. Move into R2 the value of 2. Execute. So, you can see, because these are, so we've made a mistake. Step back, step back, step back. So, these guys are the same, right? So, when we compare them, we're going to get the 0 status flag, and then BEQ is going to jump to false. This is all good. But then, and then we set R2 equal to 1. But because these are goto statements, we then fall through to the false case as well, and then R2 is overwritten here. So, in order to actually skip the instructions inside of the false block, we have to include a branch to after the false block. So, let's say end if, and let's just do the end instruction because we don't need to, and then we can branch to end if. We can also branch to end if here. Then you can see R2 is 1 in the case where these are the same, and R2 is 2 in the case where they are not. So there you go. Hopefully that is a good example for you. This is the version of that program that I have in the slides. In this program, we take different branches based on whether R0 and R1 are equal. Note the B plus EQ and B plus NE branch instructions. Here we go, right? Also notice that, true and false are labels here. They're not Boolean literals. Cool! Awesome! Also note the unconditional jumps to the end if label. While this program labels an if structure explicitly, labels may only occur once in an assembly file, so this style of labeling may not be practical. So inside of an assembly file, each one of your labels has to be distinct, because, if you had multiple labels that were the same, the assembler wouldn't be able to decide which one of those two that you wanted to actually jump to. So each one of these has to be unique. So if you want to write a program with more than one if statement, spoiler alert, that's entirely probable. This might not be a good way of going about it. Minimally, you should have like if 1, if 2, if 3, etc., etc. So let's consider some things, though, to try to increase the efficiency of this code, right? In assembly programs, the efficiency of a piece of code is directly the number of instructions. In C, it's kind of like, there's not necessarily a strong correlation between the number of C statements and the efficiency of the program, but in assembly, the fewer instructions you are executing, the fewer instructions are actually getting sent to the CPU, which means that means less time and more efficiency. So, using some knowledge about the way in which branching works and the way in which goto works, we can actually make this into a more efficient program, and in so doing, hopefully illustrate some points about how branch instructions actually work. So, first of all, line 5 is redundant. If line 6 does not jump to line 10, then execution will just pass through it into line 7 anyway, line 7, 8, and 9. So, we can actually just remove it entirely. We don't have to jump there. As I will demonstrate, our algorithm works exactly the same in both cases. There you go. So that's one optimization. That jump doesn't need to be there. Now, here's another question. Is this label necessary if there are no branching statements that lead to it? Possibly, if you might be writing if you're still in the middle of writing the code, and you may want to jump back there at some point. But if we consider this to be a finished piece of code, the true label doesn't actually have to be there because it's never used. And you can see that doesn't change anything. In this example, the if label is in the same category. Similarly, the jump on line 12 is also redundant. We are jumping to the next instruction. You don't have to do that. That's redundant. So let's remove it. And you can see nothing has changed. While this code is more efficient than the code on the previous slide, we've taken a major hit in terms of readability, particularly as the scallywag who wrote this code didn't leave any comments. Often the purpose of writing in assembly is to perform these sorts of optimizations, at the expense of readability. This is one of the reasons assembly code has a reputation for being difficult and is used by a small number of people. Assembly programming is a highly specialized skill. If you're going to program assembly code professionally, you basically have to memorize vast tracts of the specification documents. You have to have an intimate knowledge of these processors. So, there you go. Cool. So, let's go back to an earlier example, and rather than relying on the implicit flag setting with the subtraction plus S operation, let's do this. This is the same thing, but using comparison, the comparison operator, explicitly. So we move 0 into R0, we move 10 into R1, add R0 as R0, R1, subtract R1, R1, 1. Notice this is subtract, not subtract S. We then compare R1 and the literal 0 to see if R1 has reached 0, and then branch not equals back to repeat, and then we repeat that entire chunk of code. There we go. Are there any questions? I'm going to wait for questions this time, because the next topic is kind of its own thing, and I want to make sure that everybody has an opportunity to have their questions answered before we get there. Ah, somebody liked that. Like and subscribe. Like and subscribe. Okay. It doesn't seem like anybody has any questions at the moment, so we'll continue on. So, let's talk memory. So far, all we've been doing is register manipulation. This is fine, but the amount of data that can be stored in registers is pretty small relative to the amount of data that's often worked on with programs. Not to mention, you've got this whole RAM subsystem inside of your computer. We might as well learn how to use it. In order to understand this kind of stuff, in order to understand how memory works in assembly, you guys gotta flex your pointer brains. You gotta recall all the pointer stuff that we've been doing up to this point, so to speak, in class. So, up to this point, we have been working exclusively with register memory, but other types of memory exist too, Alright. I do have a question. Is there a midterm 2? Sorry, joined the lecture a little late. No. No, I don't think it's going to be feasible. No. There isn't going to be a midterm 2. I wish. Yeah. Anyway, over the next few slides, we'll see how to A. Declare and initialize regions of memory. B. Find the addresses of declared memory cells. C. Load data from memory into registers. And D. Store data from registers back into memory. The key to understanding this process is that only registers may execute data manipulations. Add only works on registers or things in registers. You can't add things that are still in RAM. They have to be loaded from the RAM into the registers, operated on, and then put back. If you try to put data that's still in the RAM, into an add function or something like that, you'll cause problems, and you may not know why those problems happen. C handles these procedures in such a manner that it looks like you are manipulating the main memory directly, when that's technically impossible. So, in C, when you work with variables, those variables are stored in the RAM. C is very good at making that process so transparent that it doesn't look like it's even happening. You, the user, can mentally abstract yourself away from the registers and having to load data into the registers. You can think of yourself as just directly manipulating the RAM itself. Direct manipulation of the RAM is technically impossible. It has to occur with the registers. So, in assembly, we do not have that layer of abstraction, so we have to learn how to do it ourselves. So, let's learn how to declare some data. In order to declare memory, we have a special type of statement. These are actually assembler directives and not instructions to the CPU. The assembler doesn't do much on its own, but setting up your memory for you is one of the things it can do. The dcd command assigns, it assigns myvar, in this case, as a variable. And so the difference between declaring a variable and an array inside of assembly is whether you give it a single literal here or multiple literals down here. Also notice that we do not have the octothorpe character here, so these are just straight numbers. So myvar is declared as a variable, array is declared as an array. You may declare either a single element or a sequence of elements. The numbers you provide afterwards initialize the memory. These variables may not be used directly to access the data within. There's no in-place dereferencing operator. So let's try this out then. Copio. Pasto. There we go. In Visual, if you go to Tools and then you click View Memory Contents, you can actually see a memory map, although I recommend putting it in decimal. You can see the memory addresses, or the simulated memory addresses, at which each of these values is being held. So there you go. So the address of myvar would be x100, the address of array would be x104, and these are all of the subsequent addresses. There you go. in order to load data from a declared memory region into a register, you need the following operations. You need ADR, which finds the address of a labeled of a variable, and you need to store that address in a register. Next, you load from that register from the memory address that is stored in that register to some other register, or even the same register. The ADR command is equivalent to C's ampersand address of operator, but of course, storing the result, it stores the result in the first operand, in the same way that it does with add. In this case, we are storing the address in R1. The LDR, or load register command, loads the data at the address specified by the second argument and stores it in the register specified by the first. In this example, the data at myvar77 will be loaded into R2. The square braces around R1 are equivalent to C's dereferencing operator. So, let's try that out and see how it works. Copy. Paste. Oh. Paste. Oh my goodness. That's... alright. So, if we interpret this in decimal rather than hexadecimal mode, you'll notice that... oh, that should be in hex, though. So, the address of myvar, which has a word value of 77, is being stored at hex 100. R1 has the value x100. That's established by this command. The next command loads the value at that address into the register. There you go. So, that's fine. That's all well and good. But, ooh, pointer information. There you go. You can actually, you got quick links here. I didn't see that before. So, that's fine, but how would we do the array? Let us, well, first of all, you need to load the address of the array, ADR, into, let's say, R3. Next, load into R4, why not, R3. So, you will see that the element that's loaded from the array is the first element in the array, because if you remember from C, the pointer, a pointer to an array points to the first element in the array, actually, technically speaking. If you want to access a different index, then you have to, you can do that using a comma. It looks like a second argument within the square braces. So let's try doing 1. Execute. Uh-oh, runtime error. Attempt to perform unaligned word access. So, ha ha ha. Guess what, guys? This, rather than just being able to give it a raw index, you actually have to perform manual alignment to the word size. So, the word size in this case is, an integer is 4 bytes. These are integers. So if you want to access the second index, you need to look 4 bytes down the line. Whereas C actually gave you, like, it handled that business for you by having a type system. In the case of assembly programming, you are actually having to enter these word addresses specifically. So if you want to access 4, then 8, then if you want to access these, like 4, 8, 15, 16, 23, 42, you actually have to offset by 4 each time rather than by 1. We can demonstrate that. Eight, 16, 20, I think. Did I miss one? I missed 12. Execute. There we go. Cool. And these can also be registers. It doesn't have to be a literal. So, yeah. Anyway, are there any questions about any of that? If not, I will terminate the stream. That's a little bit of assembly for you guys. Incidentally, I realize a lot of people are probably trying to finish off A4 today, so I'll try to be a little bit more present on Piazza than perhaps. I'll try to reply a little faster to messages on Piazza today. Plus my email, but please use Piazza if it's appropriate to do so. Cool. Doesn't look like any questions. So thank you very much for paying attention today. Nice to have the stream not. Oh, wait. The world if technology didn't exist. This is how I feel eating assembly. That is funny. The world if technology didn't exist. Look at all that technology. Assembly is not something you should worry too much about. Yeah, like... Well, let's just put it this way. The amount of your brain that assembly is going to require after you graduate is probably going to be far, far less than while you are an undergraduate. So, I'm not saying it's restrictedly an academic topic, but yeah. Take her easy, folks. Go get some lunch.